So now that we've had a chance to talk a bit about the concept of happens before relationships, let's take a look at a number of different examples of happens before relationships that occur in Java. And we'll be focusing, of course, primarily on things that are part of the Java class libraries, part of the Java virtual machine. And you'll see a bunch of examples that should look very familiar to you by now because we've discussed them already. This, by the way, is why I cover these topics a little later in the course, because it's kind of abstract. And until you've had a chance to play with threads, until you've had a chance to play with various synchronizers, it doesn't really sink in until we have a chance to go to it in more detail. And we'll look both at how Java threads enforce the happens before relationships, and we'll also take a look at how some of the Java collections also support happens before relationships. So we'll see a bunch of different examples. Methods in the Java thread class establish happens before relationships. And you'll be very familiar with some of these methods. So here's a good example. Starting a thread, in other words, initializing the thread, creating the stack, initializing whatever local fields and other information like thread-specific storage or registers and so on, must happen before the run hook method of the thread is called back. Obviously, if you start a thread and then the run hook method is called back before the thread is properly initialized, you could only expect chaos and insanity to ensue. So here's a very simple example to illustrate how this works. You can see here how we're going to make ourselves an instance of thread called thread B, and we're going to go ahead and give it some lambda expression to run. That's not very interesting here, just something to do in its run hook method. We then go ahead and start thread B. And let's assume, for sake of argument, that thread B is started in the context of some other thread, thread A, or the main thread. This lambda expression will play the role of the run hook method. So that's going to print out hello world in a background thread. Clearly, we need to have thread A's call to the start method of thread B happen before thread B's run hook method is called. So obviously, start has to occur in thread A before the run hook method can be called back. That's pretty obvious. But maybe what's not so obvious is that thread B must be fully initialized before the hook method for the run lambda expression here gets called. And again, it's just a guarantee. It's kind of an obvious guarantee, but it's a guarantee nonetheless that things will occur in the right order and happen before. So there could also be other state that's associated with thread B. Thread B might, in this particular case, there really isn't any other user-specific state, but there could be if you have your own thread with its own fields. But at any rate, the state, the system-level state of thread B has to be consistent and visible to the run hook method before it begins to execute. At the other end of the spectrum, we have what happens when threads join. One thread joins with another. And so the termination of a thread must happen before the join method can return, indicating that the first thread has finished. So let's take a look at an example of this, very similar to what we had before. We go ahead and create thread B and start it. And obviously, thread B will terminate after the run hook method, the one that prints hello world, completes. And thread A, which is the one that created thread B, will wait on join, and that will only continue running. In other words, you'll only return from join after thread B terminates. Can you imagine what would happen if join returned before thread B terminated? That would be very confusing and inconsistent. So that's another guarantee you get from the Java threads package. Likewise, after join returns, thread A must be capable of seeing any changes made to shared state that occurred in thread B. So it has to, again, be propagated properly from thread B, which of course could be running in its own core with its own cache. All state changes that are shared between thread A and thread B must then be made visible to thread A after the join returns. So you can see, again, there's some implicit synchronization taking place under the hood that's flushing caches and making sure that the memory is properly pushed out in a way that's consistent. So those are some examples of happens before relationships with Java threads. Let's also talk about the happens before relationships related to Java collections. So there's a whole bunch of methods in the Java util concurrent package. And these belong to various classes, some of which we've talked about in detail, like array blocking queue, some of which we talked about briefly, like concurrent hashmap, and we'll get a chance to talk more about those in our upcoming assignments. So these also, of course, enforce happens before relationships too. So here's a very simple example. The release of a monitor lock, if you're using just good old synchronized methods and synchronized statements in Java, happens before every subsequent acquire on the same lock by some other thread. So if we have thread A and thread B, and they both use synchronized statements or synchronized methods, then as you can see here, the release of the lock by A happened before thread B is able to acquire the lock. And then in some ways, that's just sort of an obvious statement of the way in which synchronization works. But what may not be quite so clear is that the state must be properly flushed and made consistent between the different threads, which of course are typically accessing mutable shared state within the monitor object itself. And so in this case, I'm kind of showing a synchronized statement, but the same behavior occurs with things like reentrant lock or reentrant read-write lock and so on. Here's a very simple example to make this point even a bit more concrete and tangible. So we've got thread A and thread B, and they're basically calling methods on the array blocking queue. In this case, we have the put and take methods. And the put and take methods are ones we've already looked at in terms of their implementation in earlier lessons on the Java condition object and Java reentrant lock. So this should be very familiar to you at this point. You can see here that any actions that occur prior to releasing the reentrant lock, in other words, updating the state that is necessary to put an item into the array blocking queue, must happen before and thus be visible to anything that occurs after thread B successfully acquires the lock. Of course, they're coordinating by having a shared reentrant lock, and thread A and thread B are sharing that lock. They're also sharing a couple of condition objects as well. And the things that are done within the put method in thread A must be properly consistent and published, if you will, to other threads like thread B when it acquires a lock and then goes to access that shared mutable state. There's some other examples. If you have actions in a thread that occur prior to placing an object in a concurrent collection, like a concurrent hashmap, they have to happen before actions that subsequently access or remove that element from the collection in another thread. So we're going to talk in more detail later today, probably, about Java concurrent collections. And here's just a simple example of where this applies in those contexts. And don't worry if some of these things are not familiar to you yet. We're going to cover them here shortly. So let's assume, for sake of argument, we create ourselves a concurrent hash map. And as we'll see here, again, in an upcoming lesson, a concurrent hash map is a map that supports concurrent retrievals and very highly efficient concurrency behavior and optimizations for updates, for reads and writes, and so on. And then we have two threads, T1 and T2. In thread T1, we're going to put some value in the map under some key. And in thread T2, we're going to get the value of that key. And of course, placing the key value pair and the element therein, the entry in a concurrent hash map, must happen before and be consistent before some other thread can access or remove the element from a map. And again, that's kind of obvious. Imagine what would happen if you could put the key in the map, but the value hadn't quite propagated, and then you go to get the item in another thread, but the value hadn't propagated through the memory hierarchy yet. That would lead to complete chaos and insanity. The way that this works, of course, under the hood is that the Java class libraries are chock full of very optimized synchronizers like compare and swap operations or var handles or atomic operations or reentrant locks or whatever that ensure that the happens before relationships are properly preserved. The good news is you, as an application developer, don't really need to understand all these nitty-gritty details, although it'll make you a better person and a better programmer if you do. You just have to understand how to use synchronizers properly. So that's the end of our discussion of the happens before relationships and the examples that occur both in Java threads as well as in Java collections and other class libraries in order to be able to demonstrate how happens before relationships occur in practice.